So here's our summary. Limiting reactant, a reagent, right, makes the least amount. The theoretical yield then is the amount made by the limiting reactant. Actual yield, you got to do the experiment like the copper lab, right? You got an actual recovery of that copper, and then you can calculate a percent yield. I think this, yeah, we did this problem too. All right, so now we just applied those same concepts to an actual chemical reaction. We have titanium reacting with chlorine to make titanium chloride, and then found the limiting reactant and theoretical yield if we have 1.8 moles of titanium and 3.2 moles of chlorine. So that was the math for that. We found that the chlorine, even though we started out with more moles of chlorine, because in the chemical reaction we use up 2 moles of chlorine, we use up twice as much chlorine as we do titanium to make the titanium chloride, that the chlorine actually runs out first. And with that amount of chlorine, we can only make 1.6 moles of titanium chloride. Then that becomes our theoretical yield, because that's what comes out of our limiting reactant. All right, so that was all review. So if we have this reaction, we have sodium reacting with fluorine gas. If we begin with 4.8 moles of sodium and 2.6 moles of fluorine, what is the limiting reactant and theoretical yield of sodium fluoride? And the way you do these problems is you just do 2 stoichiometry problems. So we're going to start with 4.8 moles of sodium, and this is why the nomenclature is important, and 2.6 moles of fluorine. That's going to be F2. So 4.8 moles of sodium. Actually, don't even need to go that far. So how do we get from moles of sodium to moles of sodium fluoride? How do we convert that?
Did you put 4.8 moles of sodium on the bottom?
4.8 moles of sodium is what we're starting with.
Oh, so it would be, okay.
So we already have moles, so we're starting from here, right? And we want to get to here. We don't even need to go as far as grams on this one. And so we don't need any molar mass because we're already in moles. So the ratio of sodium that it takes to make sodium fluoride is 2 moles of sodium to 2 moles of sodium fluoride.
So then would you put 2 moles of sodium on the bottom?
Yeah, 2 moles of sodium on the bottom.
I was like looking up at the ones that we did before and I was like, kind of going off that.
Yeah, in all of the ones that we did before, or in a lot of the ones we did before, especially leading up to limiting reactants, we started at grams.
Yeah, like with the pancake stuff.
Mm-hmm. So if it helps, you can think of this as like a road map, right? And you're looking at the map and you're saying, oh, we're starting at moles, so we're starting from here. Rather than if we were given grams, and you have to start back here. So we're actually closer to a solution starting at moles. And then this one's easy because 2 divided by 2 is just going to be 1. So if we multiply 4.8 by 2, divide it by 2, we're going to get the same thing back out. So 4.8 moles of sodium fluoride is going to make 4.8 moles of, or sodium is going to make 4.8 moles of sodium fluoride. And for these easier problems, I would encourage you to just write them out. Even though you can look at this and you can see it, remembering the structure of how to write this out and why it's written out this way so that our units cancel. So we have moles of sodium cancels out with moles of sodium, and then our units are moles of sodium fluoride. That's super important for doing problems further down the road that might be more complicated or have more complicated ratios. All right, and then so that's how much sodium fluoride we can make. And remember, this is assuming that we have more than enough of everything else needed for this reaction. So we're saying, okay, if we have this amount of sodium, let's assume we have an infinite amount of fluorine, how much can we make? And so now we're going to reverse that question and say, now we've got 2.6 moles of fluorine. How much sodium fluoride can we make, assuming that we have more than enough sodium? So what's the ratio here between fluoride and sodium fluoride? One mole of fluorine to 2 moles of sodium fluoride. Because there's a coefficient of 1 in front of that F. So if it helps to write in those coefficients of 1, you can do that. And so our 1 mole of fluorine goes in the bottom. 2 moles of sodium fluoride on top. Again, because we're canceling out these units. So moles of fluorine leaves us with sodium fluoride. So it's going to be 5.2 moles of sodium fluoride. So which of these is our limiting reagent? What do we run out of first? Sodium runs out first. We know that because it makes the smaller amount. So sodium is our limiting reagent. And what's our theoretical yield? How much sodium fluoride? Oh. No, it's going to be this amount of sodium fluoride that can be made with our limiting reagent. So this is our theoretical yield. All right. So this is, in a lot of ways, an important question to ask in industrial situations, or even if you are baking. Like, some things are more expensive, so you want to make sure you get just exactly as much as you need of, if you're making a pie, I guess, like a peach pie, like how much, the peaches are probably the most expensive ingredient, so you're going to buy just as many peaches as you need, whereas like flour and baking powder and all the other things are going to be super cheap, so you can buy those in bulk and put them on the shelf. In industrial applications, the limiting reactant is chosen to be whatever's the most expensive thing, because they don't want to buy any more or use any more of the most expensive ingredients than they have to. So they'll throw those in, or they'll use the whatever is hardest to remove. So if there's something that does get left over that's going to be really difficult to remove from the mixture at the end, that needs to be the limiting reactant so that it gets used up by the end of the reaction so they don't have to remove it later. And now we're just really going to take this idea of limiting reactants and do these problems just starting from grams instead of moles. And that's when it makes it more difficult to see just from looking at the problem which one's going to run out first, because now we have to use molar mass to convert grams to moles to figure out how many of each species in the reaction we have. So we've got sodium reacting with chlorine to make sodium chloride. If we have 52 grams of sodium and 65.8 grams of chlorine, what are the limiting reactant and theoretical yield? And we're going to be able to find those at the same time, because when we find the limiting reactant, then we've also calculated our theoretical yield. So it doesn't matter which order we do these in, but we have to calculate for both of them. If we have 53.2 grams sodium. What's the first step here? We're starting here, grams of A.
Find the ratio.
We do need that, but we are in grams first.
So would you find the molar mass in grams? No?
Yes, the molar mass, to convert it from grams to moles. Yeah, so we got to do this first step, right? These are both A, so we use the molar mass to get from grams of A to moles of A. So for sodium, it's easier, or easy, or you're going to look at the periodic table. And I'm going to use just 2 decimal places, so 22.99. And then, so that's 22.99 grams of sodium per mole of sodium. So where does the 22.99 go? On the bottom. Grams of sodium per 1 mole of sodium. Now what do we need? Now the ratio. Yeah, so what's our ratio between sodium and sodium chloride? 2 to 2. 2 sodium to make 2 sodium chloride.
So is it like when you're finding the ratio, it's not just on the reactant side?
It is not just on the reactant side. It'll be from the reactant. So this is a synthesis reaction. So we got 2 things coming together to make 1 product. We can have this and do these calculations for reactions where you'll have 2 products, like a double displacement reaction. And then you just need to make sure you pick the same reactant or same product to calculate to for both of them. We'll see examples of that.
Okay.
We'll do examples of that. But for now, the ratio, so it's going to be 2 moles of sodium chloride on top, 2 moles of sodium on the bottom. So we've done grams of A to moles of A, and now we've done moles of A to moles of B. So what's the last step? Grams of, so we have moles of sodium chloride.
So now you do the chloride?
Well, now we need to convert this last step to go from moles of B to grams of B.
So would you find the molar mass of sodium chloride?
Yeah, molar mass of sodium chloride. So we know the mass of sodium is 22.99. Chloride is 35.45. Double check that, yeah. That's grams of chlorine per mole of chlorine. So those 2 added together, 35.45 plus 22.99 is going to be 58.44 grams of, not chloride, sodium chloride per mole sodium chloride. So here, even though it doesn't explicitly say find how much sodium chloride there is, that's our only product. So our theoretical yield has to be, or our limiting reactant, we're going to find by calculating the amount of sodium chloride that's made. And then the theoretical yield has to be of sodium chloride. Yeah.
I was just about to ask that. On the test, would you, like if we stopped at like moles, would that be a problem if it didn't explicitly say that you wanted the grams of sodium chloride?
Great question. And that would be fine. So if I don't specify what I want the final answer to be in, it's kind of fair game. You could go to grams or you could stop at moles. Because you could tell me the theoretical yield in moles of sodium chloride. And you don't actually have to calculate out to grams to figure out which one is the limiting reactant, because if it makes a smaller number of moles of sodium chloride, that's going to be a smaller mass of sodium chloride. But yeah, I will specify the units that I want for the final answer. And if I don't, again, fair game. But I will try to always specify the units of the final answer and tell you what I want you to calculate it of. So if we had two products, I would say, what's the theoretical yield of product A or product B? Okay, so we can calculate this. So 53.2. Remember, this isn't going to be our final solution here. We still have to figure out how much sodium chloride we can make with the grams of chloride that we were given, or chlorine that we were given. But we can calculate this one out for now and then compare later. So 53.2 times 2 times 58.44 divided by 22.99 divided by 2. And that's going to be 135. I guess that's how many sig figs we have. This should be 1.35 times 10 to the 2 grams of sodium chloride. Now we're going to do another stoichiometry problem, but this time starting with grams of chlorine. So remember that the only thing that really makes stoichiometry problems different from other stoichiometry problems, different from each other, is the fact that you need different molar masses because they're different compounds, and you have different ratios because, again, different compounds. But those are all coming from either your balanced chemical equation or the periodic table. So you can fill those numbers in, but it's going to have the same structure. They're all basically going to have the same structure. So here we need to go from grams of chlorine to moles of chlorine. So how do we do that?
Put 1 mole of chlorine on the top and 35.45 grams of chlorine at the bottom. Can we use a 35.45?
Almost. So is it Cl or is it Cl2? Yeah, you got to times 35.45 by 2. It's a curveball, I know. Those Brinkelhoff compounds were always tricky for me also. So if it helps, always write it out, Brinkelhoff. BRINCLHOF. In their elemental form, these are all diatomic. There's always 2 of them. Now here in our balanced chemical equation, it shows you that, Cl2. But if you're given a problem that said chlorine gas, and I haven't looked at, I don't remember all of the questions from the chapter, but I can almost guarantee that there's going to be one that does that to you. So I know, another thing to remember. And then, so now we've got moles of chlorine. How do we get from moles of chlorine to moles of sodium chloride?
We have 2 moles of sodium chloride on top
Mm-hmm.
and 1 more mole of chlorine.
Yep. 1 more mole of chlorine on the bottom, right? And now, from here on out, this is going to be identical to the previous problem because we've gotten to moles of sodium chloride, and so we're going to do this exact same last step to figure out how many grams of sodium chloride that is. It's the same compound, so we use the same molar mass. but we're starting all of these calculations with a different number. So this will just be, let's copy this from the top one. So we'll start with 65.8 times 2 times 58.44 divided by 70.9. And that's going to be 1.08 times 10 to the 2 grams of sodium chloride.
So chloride would be the limiting reactant.
Yeah. Chlorine is going to be our limiting reactant. And what's our theoretical yield? What? Yeah, the 1.08. So this is our theoretical yield.
Like this stuff wouldn't be so hard, but there's so many like little sneaky. You know what I mean?
In terms of molar masses, the one sneaky one is the Brinkelhoff compounds because they're I2. You can always look though, especially if I give you a balanced chemical equation, right? You can always look up here to see, okay, sodium, that's just one sodium. Don't have to worry about that. It's just 22.99. Chlorine, though, it says Cl2, so that has to be 35.45 times 2 to get the molar mass. If you're going from just names to formulas and writing out a problem, then it's a little trickier. Also, I wanted to point out so that when we have two numbers that are in scientific notation and we want to compare them quickly and easily, this is where scientific notation becomes more of a tool and less of like strict rules about when to use it and how to use it. So when we're comparing these two numbers, if this exponent on 10 is the same, we can compare them just like any two numbers. So like if we had 5.7 and 3.4, right, we can compare those two numbers just by looking at them and say, oh, 3.4 is smaller. But if this is 3.4 times 10 to the 3, and this is 5.7 times 10 to the 2, those different exponents mean that these are really hugely different numbers. And if you want to be able to compare them more easily, move the decimal place, change the exponent so that the exponents are the same. So this 3.4 times 10 to the 3 would be, if we move the decimal place over to the right one, would be 34 times 10 to the 2.
So then we make it bigger?
Yeah, so now that these exponents are the same, we can look at this and say, that's 34, that's bigger than 50, or 5.7. Because these numbers, maybe I should have started with this. Because 5.7 times 10 to the 2 would be 570. 3.4 times 10 to the 3 would be 3,400. So these both mean the same thing. They're both 3,400, but we're just changing the exponents here. And so this is where you can be intentional about the exponents that you choose so that you can compare these two numbers more easily.
So we would have gotten it wrong if we would have said that 3.4 is the limited reaction. In our eyes, that looks like a smaller number.
Yeah, if you were to just look at both of these and ignore the exponents and you're like, oh, well, this is smaller. It's actually a lot bigger. So that's where you can manipulate the scientific notation to make numbers comparable. Or you could always just write them out in just like full decimal form before you compare them. That works too. Okay.
Or can you assume since it's 3, it's bigger than the 2, so then that one's the smaller, that one's the bigger?
Yes, you can also do that.
without having to do all that? So if you see that the exponent's higher than you want it to be, you're gonna, that
Yeah.
10 to the third.
Unless you wrote one of these. There are some weird situations that you get into, but yes. If in general, 99.9% of the time, larger exponent, larger number. Okay, so here's another way of phrasing a limiting reactant problem. And probably the wording that is the most, or causes the most confusion, because it says, what maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of helium, or hydrogen. Also note, right, these are N2 and H2. So this is a limiting reactant problem. Nothing changes, just the way the wording, the way the question is worded changes. So how do we start this problem? We're given two numbers.
So you would start with the grams of
Yeah, that's fine. You can say N2, it's fine. You should try and say the name nitrogen, yes.
I was gonna say it, but.
Yeah, you're almost there. And this raises another question though, like, does it matter which one you start with? Doesn't matter which one you start with. You're gonna do both of them eventually. So it doesn't matter where we start, but since nitrogen's written first, sure, we'll do nitrogen first. That's what I would normally do. It's just, don't waste your decision-making power on decisions that don't matter. Of course, it requires that you know it's a decision that doesn't matter, but it comes with some practice. Okay, so we're starting with grams of nitrogen. Where does that start us on the roadmap? So we got to convert grams of nitrogen to moles of nitrogen. Yep, so yep, 14.01 times 2. So this is going to be 28.02, and it'll get you like that. And so nitrogen, N2, is going to be 28.02 grams per mole. Excellent. Now,
To do the ratio.
ratio, yes.
There's 2 nitrogen and 2 hydrogen, so 2 to 2. Yeah, every time.
Yeah, no. So don't use the subscript. Completely blanked on the number. It's the coefficient, so the numbers in front that tell you the ratio. So you need 1 N2, and that will make 2 NH3.
So the coefficients tell you the ratio, not the subscripts.
Yeah. 1 mole of N2, 2 moles NH3. Yep. This is the nice thing about stoichiometry versus other unit analysis problems. We're always converting the number or the units on top. So if we always have units on top, then we always cancel them out by putting those same units on the bottom of the next sort of cell in this stoichiometry table. And now we go to grams. So yeah, now we've got N, H, because we're doing ammonia, NH3. So 1 nitrogen, 3 hydrogens. I guess I could do this. So 17.04 grams per mole NH3.
Would you multiply it by 2 because there's 2 moles?
Ooh, very good question. The answer is no. It's a great question. No, it's a great question because it comes up a lot. A lot of people have done that on stuff and never asked that question. But so we take care of those coefficients and like the fact that there's 2 moles of NH3 in the reaction with this part of our calculation. So because we put the 2 moles of NH3 here, we don't need to think about that when we're going from moles of NH3 to grams of NH3. It's only if we're calculating the molar mass, that's when we look at the subscripts for how many of each. Okay, so we're going to do 17.04 grams on top or bottom? Yeah. Yeah, because we want to keep grams of NH3 and we want to get rid of 1 mole NH3. I actually need to move this up a little. Great, so that's calculated. We've gone through this whole thing, right? Started with grams of A, calculated moles of A, went from moles of A to moles of B, coefficient ratio, then from moles of B to grams of B. So we figured out how much ammonia we could make, assuming that the nitrogen is limited and we have enough of everything else. So 25.2 times 2 times 17.04 divided by 28.02. So it's going to be 30.6 grams NH3.
But then you have to multiply it by a unicorn or something.
3 dogs, actually.
3 dogs.
No.
Okay.
Yeah, that is the final answer.
Is there a specific breed or?
Or final answer of this part. So what's next?
So then we have to do the same thing for hydrogen?
Yep. Same thing for hydrogen. So we'll start with 8.42 grams of H2. What's going to be the molar mass of H2? Yeah, 2.02 grams of H2, 1 mole of H2. And our ratio here, hydrogen to nitrogen, or hydrogen to ammonia.
1 mole of nitrogen equals 2.
Hydrogen,
Oh, yeah, 3.
3 moles of hydrogen. And that's going to be 2 moles of NH3. And now, the final calculation is the same as the previous problem. So you can save yourself from some time, because you don't have to recalculate the molar mass of ammonia. (8.42 times 2 times 17.04 divided by 2.02 divided by 3. So that's going to be 47.3 grams of NH3. Now this is where the wording of the question might lead you to the wrong answer.
So you need the bigger one. Because you need the mass
Well, what is our assumption when we calculate this amount? Right, we're assuming with this amount of hydrogen that we have enough of everything else. But if we do the same thing with nitrogen, we only get 30.6 grams of ammonia. So we run out of ammonia before we could make this amount of, or we'd run out of nitrogen before we could make this amount of ammonia.
So your maximum would be, yes, sorry.
Yeah, so your maximum amount is still the limiting reagent.
The whole thing is a facade.
So our limiting reagent is nitrogen, and the maximum amount we can make, because we would run out of it, is going to be our theoretical yield, which is 30.6 grams. This problem also does a nice job of highlighting the fact that even though we started out with way more mass of nitrogen, because nitrogen weighs so much more than hydrogen, there's actually fewer moles of it. And then between that and the ratio, which actually the ratio doubles it, right, we end up with a smaller amount of ammonia from 25.2 grams of nitrogen versus the 8.42 grams of hydrogen. This is also why NASA would love to use hydrogen for all of their rockets as fuel, because it's really, really light. It's really, really energy dense because of that. But it has all kinds of other problems. Mostly the fact that it is so small, it leaks out of everything. So if you see maximum amount, or if you see what is the most you could make, and you're given the quantities of two reactants, you need to find the limiting reagent. It's still a limiting reagent problem. Because this is like, how many pancakes could you make if you had these ingredients? Well, whatever ingredient you ran out of first.
Basically, whatever you think it's gonna be, it's the complete opposite. We're gonna do very
Okay.
on this test, Dr.
I believe in you. I believe you. Okay. Perfect. So now we're getting a chemical reaction where we have two different products. And we're also given, and this is important, this will guide the way we decide how to do things here. We're given an amount of iron. So iron is one of the products. Right, so this reaction, the reaction of 185 grams of iron oxide with 95.3 grams of carbon monoxide produces 87.4 grams of iron. And then it says find the limiting reactant, theoretical yield, and percent yield. Remember, those three things are all tied together, because when you find your limiting reactant, right, the thing that you run out of first, then however much of your product that you're looking for makes is your theoretical yield. And then your theoretical yield and the actual yield, or in this, actual yield divided by theoretical yield times 100 gives you your percent yield. So those are all coming out of the same stoichiometry problem.
Does it matter which number's on the top and which is in the bottom when you're dividing?
It does. So your theoretical yield will always be on the bottom, because your percent yield is always going to be smaller than 100% yield.
So the produced would be on the top.
Yep. So this produces 87.4 grams of iron. So we still have to do limiting reactant problem. I'm going to kind of move a little bit faster through this, because we've done several of these at this point. So we're going to start out with 185 grams of iron oxide. Again, we could start with either. Doesn't really matter, because we're going to do them both. And then what are we going to be calculating towards? What do we want to find the amount of? The iron, right? So our B in this case, we have a choice. We could calculate, and this is where I was talking about the limiting reactant problems where you have two products. Sometimes in a problem like this, right, it says, find your theoretical yield and percent yield, and then gives you an amount of iron. So obviously, calculating the amount of iron produced from both of these is going to save you some time in the long run because you're going to need that number. But we could still find the limiting reactant by calculating how much CO2 is produced by both of these amounts of iron oxide and carbon monoxide. That would still tell us the limiting reactant, but wouldn't be useful for the percent yield of iron, or the theoretical yield of iron. So if your question stem gives you something like this, produces some amount of something, calculate towards that, and it'll save you time. Okay. So iron oxide, we need to find iron, which is 55.85. And there are two of those. So 2 times 55.85. Oxygen is 3 times 16.00. That's going to be 159.7. So 159.7 grams of iron oxide. One mole of iron oxide. So again, keep in mind that we are going to be looking towards iron. So our ratio, our molar ratio from our coefficients in the chemical equation to get from iron oxide to iron is 1 to 2. So we have 1 mole of the iron oxide and 2 moles of iron. And then we want to calculate how many grams of iron. So iron is not one of the Brinkelhoff compounds, and also in our chemical equation, it's just written as Fe. So we can use the 55.85 that we looked up on the periodic table to calculate how many grams. So grams of iron is 1 mole of iron. So I'm just going to calculate that real quick. That's going to be 129 grams of iron. And then we repeat this process, but now starting with 95.3 grams of carbon monoxide. So carbon monoxide is going to be just 1 carbon, 1 oxygen. So 12.01, 16.00. So it's going to be 28.01 grams of carbon monoxide is 1 mole of carbon monoxide. And then we'll use our molar ratio, this time from carbon monoxide to iron. So it's 3 moles carbon monoxide, oops, not 2, to 2 moles of iron. And then we'll just calculate how many grams of iron. Remember, if you're on your second limiting reactant, or second reactant of a limiting reactant problem, going to be the same molar ratio as the one above it. And so 55.85 is what we use there again. So we get 95.3 times 2 times 55.85 divided by 28.01 divided by 3. This is 127 grams of iron. So what is our limiting reactant? Carbon monoxide. Right? 127 is less than 129. Pretty good reaction, though, considering that we use up almost all of everything. Right? If those two numbers are close, that means that most of it's getting used up. So limiting reactant is the carbon monoxide. So our theoretical yield is 127 grams. And then our percent yield is going to be 87.4 grams of iron divided by 127 grams of iron. And really, you should use all the decimal places here, and times 100 is going to be 69.0% yield. Any questions? So all of these problems, even though they all look very different, again, they're only different because we have to use different molar masses, which all come off of the periodic table. And we have to use different molar ratios, which all come from the balanced chemical equation. And so in essence, this is the same structure for all of them. We just have to plug in different numbers. So
On the bottom, you didn't use the carbon monoxide all the way through because we're looking for iron.
you mean,
No, you stopped there and we're converting the rest to iron.
because we converted from, like here we did that too, from iron oxide to iron. And then here from carbon monoxide to iron. So even though the carbon monoxide doesn't have any iron in it, it's one of the ingredients required to convert this iron into, or to convert the iron oxide into pure iron.
So we didn't use the 3CO2 at all in the bottom?
Yeah, we didn't need to use CO2 on any of it. So we could have calculated how much CO2 would be produced. But since it wasn't asked for in the question, we didn't need to do it. So the only things that you ever need to include are your starting number, and then you calculate molar mass, molar ratio, and then the molar mass to get whatever the question's asking for. All right, gotta move on though. So I'm going to include in these chemical reactions the idea of enthalpy. Enthalpy is a measure of the heat evolved or absorbed in a reaction. So it's how much heat comes out of the reaction, or how much heat does the reaction soak up from its surroundings. And we've talked about exothermic and endothermic a little bit, right? Exothermic means it's emitting thermal energy. So any combustion reaction emits thermal energy. Endothermic reactions are more rare, but there are things like instant ice packs, chemical ice packs. So that amount of energy that gets absorbed or emitted is called enthalpy. And we can calculate an enthalpy of reaction, which is the amount of thermal energy or heat that flows when a reaction occurs at constant pressure. I don't really have to worry about the pressure stuff for now. So the sign of this delta H reaction, that's our enthalpy of the reaction. That's how much the heat changes. So it can be positive or it can be negative, and that depends on the direction in which the thermal energy is flowing. So energy flowing out of the chemical system is like a withdrawal from your bank account. It's negative. And so you're removing heat from the system. That's exothermic, negative delta H. Energy flowing into the system is like making a deposit in your bank account, and we'll have a positive sign. So if we have, let's call this the system. So that's our chemical reaction that we're interested in. If, well, it doesn't really show up. I won't do it in red. So if heat is leaving the system, it's being taken out of the system, that's negative delta H of reaction. If we have our system and heat is going in, it means it's being added to the system, so it's a positive delta H of reaction. So it's always from the perspective of the system or the chemical reaction. Heat in or heat out. I guess I write these two. So heat coming out is going to be exothermic. Heat going in is going to be endothermic. So for exothermic reactions, heat energy is released to the surroundings. And to keep that in perspective, always remember, right, if you're burning something, it emits heat. That's what exothermic is. In an endothermic reaction, you're absorbing that energy from the surroundings. So you could do these energy diagrams like this also, where higher up on the diagram you have more energy, or exothermic reactants are starting out with more energy, and that energy is stored in the bonds that are connecting the atoms in those molecules. And so in our exothermic reactions, we rearrange those molecules, and that energy gets released, and then it takes less energy to form the new bonds of the products than it did, or than there was in the original reactants. So they're rearranging to have less energy in those bonds. And so that extra energy gets released as heat. In an endothermic reaction, the opposite happens. So we have our reactants that have lower energy than the products. When they break apart, reform to make the products, when they react, those bonds between the atoms contain more energy than the reactants did. And so that energy has to come from somewhere, and so it comes from the surroundings. And these are more rare because it's harder to sort of stuff the energy. I guess you could think of it as stuffing the energy into those chemical bonds than it is to let it out. It's kind of like pressure being released. So for exothermic reactions, because energy is leaving that system, delta H is going to be negative. And the important thing here is that we can write this out along with our chemical reaction. So delta H for this reaction of burning methane, or natural gas, is going to be negative 802.3 kilojoules per, it's not usually written in, but this is kilojoules per mole. So for every 1 mole of methane that you burn, you get out 802.3 kilojoules of heat. Because this is from the perspective of the system, that heat is leaving the reaction. So it's a negative delta H, right? Negative sign. So this total magnitude here tells us that, right, the size of this means that that's how much heat is coming out of it. The sign tells us where it's going, it's leaving. And then for every 1 mole of CH4 and every 2 moles of oxygen. For endothermic reactions, the opposite is true. So we have a positive sign here for delta H of reaction. When 1 mole of nitrogen reacts with 1 mole of oxygen, it absorbs 182.6 kilojoules of heat from the surroundings. So the size of this number says just like the quantity of heat that's being moved. The fact that it's positive tells us that it's being moved from outside of the chemical reaction into the chemical reaction. And that's per 1 mole of nitrogen and 1 mole of oxygen. And then because it's tied to those numbers, so if we had 2 moles of nitrogen reacting with 2 moles of oxygen, how do you think that affects the amount of heat that gets absorbed? So if we double the amount of chemicals that we're reacting, we'll also double the amount of heat that will be absorbed from the environment. And so that's called a stoichiometric relationship. So we can calculate, just like we calculate, like if we had 1 mole of nitrogen, we could say, well, how many moles of nitrogen monoxide does that produce? We could also say if we have 1 mole of nitrogen, how much heat does that absorb? And that's set up very similar to our other stoichiometry problems. So the amount of heat emitted or absorbed depends on the amount that actually is reacting. So we usually specify delta H of reaction with any chemical reaction that it's describing. And then the magnitude is for the stoichiometric amounts of reactants and products. Right? So just like in this problem, it's 1 mole of nitrogen, 1 mole of oxygen. Those two combining makes this amount. So for a balanced chemical equation and delta H of reaction, say that 1 mole of propane reacts with 5 moles of oxygen to make, and releases, and we know it's releasing it because it's negative, releasing 2,044 kilojoules of heat. Along with the CO2 and H2O that's also produced. So just like we use the coefficients in this balanced chemical equation to calculate different quantities in the chemical reaction, we can also use that to create a relationship between 1 mole of propane and delta H of reaction. So we can say 1 mole of C3H8 will make negative 2,044 kilojoules of heat. And so just like with our molar ratios between different compounds, we can plug that into a stoichiometry and solve for how much heat is produced. So less hot reaction, we have ammonia reacting with oxygen to form nitrogen monoxide and water. You can calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So we're going to have a slightly different solution diagram, solution map. We're still starting out with grams. So we're going to have grams of NH3. Then what are we going to do first? Convert it to moles. So we'll get moles of NH3 because it's this amount of heat produced for every 4 moles of ammonia that reacts. So we could say for 4 moles of NH3, we're going to absorb negative 906 kilojoules of heat. So then we can get from moles of ammonia to kilojoules of, I always do this backwards. Kilojoules of heat. So it starts out similar because we have to get to moles because we're using ratios from the balanced chemical equation, so everything there needs to be in moles. So grams of ammonia to moles of ammonia, and then we can figure out the kilojoules of heat. So we'll start with our 155 grams of ammonia. And this is where the fact that this is just a unit conversion problem comes in handy also. So if we want to get from grams of ammonia to moles of ammonia, we've got to use a molar mass. So there's 1 nitrogen and 3 hydrogens. So that's going to be 14.01 plus 3 times 1.01. So 17.04 grams per mole. So we'll put the grams on the bottom. Moles, NH3 on top. And then because we have moles of NH3 and we have delta H and moles of NH3 in our reaction, we can figure out what that ratio is, which I've already written down. So if I put 4 moles of ammonia on the bottom and negative 906 kilojoules of heat on top, right? Unit analysis, grams of ammonia cancels, moles of ammonia cancels, leaves us with kilojoules of heat. So 155 times a negative 906 divided by 17.04 means that we are going to absorb 8.24 times 10 to the 3 kilojoules of heat. Man, we're so close. Okay, does that make sense? Stoichiometry is just unit analysis. We're just getting new conversion factors for all of them. But all of those come from either the periodic table or balanced chemical equations. So real quick, let's work through this one. And it's just reversing the question here. So it says, what mass, and that's a key word there, mass, right, means grams. What mass of butane in grams is necessary to produce 1.5 times 10 to the 3 kilojoules of heat? And also, what mass of CO2 is produced? So we always want to start with what we're given. So 1.5 times 10 to the 3 kilojoules of heat. So we want to know how much butane, again, this is one of those things where I will never just tell you, hey, butane. I'll say, because I don't expect you to know how to name butane. So how much butane did it take to make this much heat? Or will it take to make this much heat? Yeah, 4 moles. So we're going to use the, right, if we can go this way, we can also go back. Just replace NH3 with butane. So, yes, 4 moles of C4H10 on top, and then this is going to be 2,658 kilojoules of heat. We're going to leave the negative off because otherwise we're going to get a negative number of moles, and that doesn't make sense. We really only need the magnitude here. So good, so we've got that, and then we want to know the mass of butane. So it's going to be made of carbon and hydrogen, 4 and 10. So 4 times 12.01 plus 10 times 1.01 is going to be 58.14 grams per mole of butane, or C4H10. So you say 58.14 grams, 1 mole. And that'll tell us how many grams needed to be reacted to make that much heat. So 1.5 times 10 to the 3 times 4 times 58.14 divided by 2,658 is going to be 1.31. I guess we have 1 sig fig here, or 2 sig figs. So 1.3 times 10 to the 2 grams of butane. And then we can set up the same problem, but now instead of solving for butane, we solve it for CO2. So 4 moles of CO2 will be produced along with 2,658 kilojoules of heat. And then CO2 is going to be 44.01. So 1.5 e to the 3 times 4 times 44.01 divided by 2,658 is going to be 9.9 times 10 to the 1 grams of CO2 produced. And this will be that many grams of butane reacted. So these would be your 2 answers. And then we could go on, right? We could figure out, just based on the amount of heat produced, knowing that it's from this reaction, we could figure out how much oxygen was consumed, how much water was produced. With any single quantity in a chemical reaction, as long as you have a balanced chemical equation, you can figure out the quantities of everything else. It's just doing the stoichiometry and changing what B is. Oh, yeah, the final note, absolute value of heat. And then they use words to say like how much heat was absorbed, how much heat was emitted, produced, evolved even, they might say. So there's going to be a lot of different ways to say the heat went out or the heat was absorbed.